sense now at the Earth and Planets Laboratory. So Conel studies cosmic debris. I've been waiting to say that all day long. Having been a Frank Zappa fan in my misguided youth, I only wish you were wearing a Sears poncho. What do I mean by that? So Conel is interested in where volatile elements, things that are normally in a gaseous state, carbon and nitrogen and sulfur and hydrogen, how they ended up on our planet. These are, after all, the components that really allow our planet to be habitable. That's kind of what we're made of. And for modern accretion theory, it's not at all clear why we ended up with all of the water, for example, that we do on our planet. So Conel is interested in understanding where that came from, how it got here, when did it get here, how was it delivered. And by and large, Conel has spent the last 30 years studying the cosmic debris that kind of filters down onto our planet as meteorites, went to Antarctica to pick them up and study them, looks at primitive meteorites, comets, interplanetary dust particles, anything he can get his hands on to try to understand where this material came from. But more recently, we've been sending spaceships up to asteroids, landing them on the asteroids, which is just amazing, sampling and bringing it back. And this is so very, very hard to get material. And because of Conel's expertise in this area, he's selected to be able to analyze some of this material. And so he's going to tell us something about this kind of thing tonight. You're probably familiar with the Hayabusa mission, which went to an asteroid called Ryugu. And more recently, the OSIRIS-REx mission that went to an asteroid called Bennu. And I think those samples are going to be returned relatively soon.
Ryugu's already back.
Ryugu's back, Bennu's coming, September, and Conel's gearing up to look at this material. So tonight, Conel's going to tell us about a new golden age for sample return missions. Take it away.
Thanks, Mike. So, as our name implies, much of what we do on this campus comes under the umbrella term of planetary science. Now, until we discovered extrasolar planets, planetary science was solely focused on trying to understand how the solar system formed, how the planet formed, and in particular, how the Earth formed, a habitable Earth formed. Now, of course, we have to also worry about the 1,000 or so solar systems that have been found outside of our own. Thank you. Outside of our own. Is that better? Outside of our own. Many of them discovered by our very own Paul Butler, but most of them don't look anything like the solar system. That's a problem, but it's not something I'm going to talk about today. I'm going to focus on what I think is the most important part of planetary science. How did the solar system, and particularly the terrestrial planets, form? Now, for obvious practical reasons, when you're trying to study objects in the solar system, most of the time you have to resort to telescopes. Sometimes you get some robotic missions that go to those objects, but neither of those types of exploration can provide nearly the same amount of detailed information that a sample return can give us. The obvious poster child for sample return was the Apollo mission, the first and I think still the most successful sample return mission. Now, the Apollo mission in between 1969 and 1972 brought back 840 pounds of rock samples, orders of magnitude more than any other sample return mission. And because of the investment in instruments, in development of techniques, and in people for analyzing this material, it shaped a generation of sample scientists. In fact, maybe two generations, because if people like me who saw the lunar landings as a child, was determined to become an astronaut, and then when reality set in, downgraded a little bit to becoming a planetary scientist. But it also revolutionized our understanding of the Earth-Moon system. It's now pretty much established that the moon formed from the debris of a giant collision between the proto-Earth and at least a Mars-sized object. There's lots of debate about the details, but I think almost everyone agrees that is how the moon formed. And that was the last major addition of material to the Earth-Moon system. And just as an illustration of how this might happen, I have a simulation from a former postdoc here, Nikki Nakajima. So that's the orange is Mercury, is a Mars-sized object hitting the proto-Earth and then hitting it again in this particular simulation. And you could watch this and how these follow the different pixels as the light stuff, which is the metal cores of the planet, sink in towards the Earth's metal core. And the moon will ultimately form as a molten blob made out of this debris that's going into orbit. Another important result from the Apollo mission was to be able to date the impact history of the moon and then extrapolate that to the Earth, and with a bit more caution to other objects in the solar system. And as you can see, there's a dramatic, hang on, I have to get this right. There's a dramatic drop-off early on in solar system history, where the solar system started about 4.56 billion years ago. There's a dramatic drop in the number of collisions occurring on the moon's surface, and presumably also on the Earth. And so it's probably no surprise that the first good evidence for the establishment of life on the surface of the Earth happens at about this time, when at about 3.5 billion years ago. And we're continuing to analyze Apollo samples as our techniques get better and as new questions crop up. Just as two illustrations of what people are doing with these samples is here, Eric Howry, a former staff member at Carnegie, analyzed these glass spheres that were formed by fire fountaining on the surface of Mars and discovered there's water in this. Now, it's not exactly wet, but there's geologically significant amounts of water in them, which sent the theorists scurrying back to try and figure out how you can retain volatiles in such a violent impact. I'm not sure that's entirely resolved, but there are some ideas out there. Also, former director Rick Carlson and former postdoc Corliss Siu are involved in a collaboration that did some very high precision dating of some lunar rocks and concluded that the moon is much younger, 100 million years younger than people thought, which, if true, has some interesting implications for the Earth as well, because if this is sort of happening at about the same time we think the Earth had oceans, or starting to develop oceans, and it's hard to reconcile this age for the moon, such a violent impact, within a few hundred million years, or less than a few hundred million years, oceans existing on the Earth's surface. So that's an interesting thing that needs to be resolved. And we are going back to the moon after a 50-year hiatus. NASA, with the Artemis program, is planning, I believe, to try and put people back on the moon in 2025. And in fact, we've already gone back to the moon because the Chinese Chang'e 5 mission, a robotic mission, has brought back in 2020 about 3 pounds of lunar soil. And China is undergoing, just like US did in the Apollo days, is undergoing a massive investment in planetary science, and both in terms of engineering, in terms of instrumentation, and people. So to be a Chinese planetary scientist must be a very exciting time at this point. Now, another sample return that gets people very excited is Mars sample return. It always seems to be just over there in the mirage, a mirage just on the horizon. At the moment, NASA is saying no earlier than 2033. And when people say no earlier than, you know, it means probably a lot later than 2033. Nevertheless, the Perseverance rover is motoring around Jezero crater on Mars, collecting samples. And here I have a sort of rogues gallery of some of the samples it's collected. I think the ones that actually stashed are either outlined in red or in green. As you can see, that I think at the moment it's collected about 18 rock samples that we would like to bring back if we possibly could. These are ones that are deemed of high scientific value. Now, the plan is, as I understand it, although it's certainly not set in stone, is that the rover will go and meet the lander, hand over the samples to the lander somehow, and they will come back to Earth. However, as a precaution, what they've done is for some samples, which they took two samples of the same rock, they have deposited some of those on a nice flat spot in the crater. And this is a sort of depot, which is a backup. If something happens to the rover, it breaks down or whatever, it falls down or whatever, and it cannot go to the rocket, and the rocket cannot land near it. The rocket, the sample return rocket, is intended to come down here and pick up the samples. It's still not clear how it will pick the samples up. There's a talk of having a little helicopter with a grappling tool underneath it that will pick them up and take it over. So everything is up in the air at the moment. It's extremely expensive and very complicated to do, but it'll be very exciting if and when that actually happens. Another amazing thing that Perseverance did was take this wonderful, I think a wonderful video of the eclipse of the sun by Phobos, one of Mars's two small moons. To be able to do a video an eclipse from another planet is just spectacular to me. And I bring this up because the Japanese are planning on bringing back a sample of Phobos in 2029. And the idea is to try and understand, how did Mars form? Is it a captured asteroid, which some people believe? Is it the product of an impact, a sort of a smaller, much smaller version of our moon? Or is it something else completely? I think this is very exciting, and will be probably our first sample return from the Mars system anyway. And 2029 isn't so long, even for me. So. But as exciting as these future sample return missions are, I want to spend the rest of this talk just describing, as Mike said, some asteroid sample returns. And really the idea of these asteroid sample return missions is to ground truth asteroid meteorite links that people have tried to make. So just a bit of background. Asteroids are the remnants of the first sort of large bodies. We think of the remnants of the first large bodies of a few hundred kilometers across that formed in the solar system. And they were the sort of building blocks, the fundamental building blocks for the planets, certainly the terrestrial planets, and probably at least some component of the giant planets. The asteroids that survived that process are largely stored in what's called the asteroid belt between Jupiter and Mars. So this is Jupiter's orbit here, this is Mars's orbit here, and the green dots are the ones that are in the main asteroid belt. The asteroid belt seems to have been a region of relative stability during this very violent process of planet formation. And asteroids from all over the solar system seem to have been scattered into this region and stored there. So in principle, at least, if we could really understand both the orbital properties and the chemistry of the asteroids, we could provide a really strong pretty strong constraints for models of at least the terrestrial planet formation and probably giant planet formation, because Saturn and Jupiter would have scattered some material into from the outer solar system into the asteroid belt. We have samples, as Mike said, of proved very difficult to make a link between the different types of meteorite we find and the different types of asteroid that the astronomers find. I should have said that you cannot determine the chemistry of an object with a telescope. You have to have a sample. Either you have to do an analysis in situ, or you have to bring a sample back to the Earth. I don't know if you can see these are these reflected light spectra that the astronomers try to use, and these are idealized versions of them, to classify the asteroids. And if you, at the back, you may not be able to see, but there are some for many of these, there's some pretty subtle features that they're using. And this is without noise from doing real measurements. And part of the problem with trying to link the meteorites to the asteroids is that many of the primitive, most interesting meteorites, particularly the ones we think were scattered from the outer solar system into the asteroid belt and may be the sources of the Earth's volatiles, they don't have a lot of features in them intrinsically anyway. And then there's this process called space weathering that all airless bodies undergo, where they're bombarded with solar wind, solar UV, micrometeorites, galactic cosmic rays. It's a pretty brutal environment at the surface of an airless body. And these things can dampen or even wash out features. And so some of the variation we're seeing here may just be due to how old that surface is and how much space weathering it's had. So we really need to have samples of a few asteroids that we can ground truth the telescopic measurements and the meteorites and make a link between them, understand the process of space weathering. And I should also say there's another complication, and that is meteorites weather in the terrestrial environment, even if they're in a lab, unless they're kept under dry, oxygen-free conditions, they will weather, and that will change their reflectance properties as well. So bringing back some pristine samples from an asteroid is the ideal way for ground truthing, trying to make this link. And that is what 3 missions have been trying to do. So 2 missions have come back, and I'm going to only talk about them briefly, and then we're going to spend a bit more time on the OSIRIS-REx mission that is coming back in September. I personally, and not many people on campus, I don't think were involved in the first mission. That's the Hayabusa mission to the asteroid Itokawa. Itokawa is a S-class asteroid. We've thought for a long time these asteroids were linked to the most common type of meteorites, so-called ordinary chondrites. But it was primarily really an engineering mission. It was the first sample of sort of spacecraft mission that the Japanese had designed, certainly to bring back samples. And despite many mishaps, they brought back about less than 1 milligram of material, tiny little grains. But with modern technology, that's more than enough to actually say, yes, this asteroid is linked to one type of ordinary chondrite, and to start to understand the physical processes associated with space weathering. The second Japanese mission, the Hayabusa 2 mission to the asteroid Ryugu, in the middle one, that went flawlessly. So they learned their lessons from the first mission. And also this mission was a great practice run for how you do international science with tiny samples. How do you ship them to people all around the world, as well as within Japan itself? And that proved essential for when the Hayabusa 2 material came back in the middle of the pandemic, which just, but it's incredibly successful. I forget how many papers have come out so far. I think it's 20 or 30 in high-profile journals in the last year or so. Anyway, my personal highlight for that mission is that what they found, I should say, the C-type asteroids are one of the more common and thought to be more primitive asteroids, again, thought to be coming from the outer solar system. They've been linked to this family of meteorites called the carbonaceous chondrites, but which ones was not entirely clear. What they found was that Ryugu is closely related to a rare but very important type of carbonaceous chondrite, the CI chondrites, or Iduna type carbonaceous chondrites. And the reason they're important is that in terms of their bulk composition, elemental composition, they have compositions that are almost identical to the sun, except for the really volatile elements like hydrogen, helium, and to a lesser extent, carbon and nitrogen. And the reason that is important is that in many cases, we use these meteorites to define the solar composition rather than the spectroscopic measurements done telescopically, because they're more accurate. And we can also say something about the isotopic composition of the solar system, which you can't really do astronomically. The C-type chondrites are also very important because, as I said, and Mike said, we think these are good candidates for the sources of the Earth's volatiles and the volatiles for the rest of the terrestrial planets. The fact that this C-type of asteroid, which is common in the asteroid belt, looks like a CI chondrite, strengthens at least the case for it being potentially a source of the Earth's volatiles. Now, what we did find is that the material coming back from this asteroid is much more diverse than we see in the four carbonaceous CI carbonaceous chondrites that we have in our collections. But it has, and it clearly shows that those CI chondrites have been badly weathered by just sitting in the terrestrial environment. Nevertheless, it's clear that the water now in clay minerals is indigenous to the meteorites, as is the abundant organic material we find in these meteorites. And if these are the sources of the volatile elements, the carbon and nitrogen and much of the hydrogen that we find we have in our bodies and in the Earth, it comes from organic material in this type of object. So then moving on to the OSIRIS-REx mission. As I said, that's coming back in September, if everything goes well. It's coming from a B-class asteroid. Now, B-class asteroids are interesting. We're not sure what, they're sort of similar to C-class, but they're a little different. We're not sure exactly what type of chondrite, primitive meteorite they belong to, probably a carbonaceous. But what's really interesting is that in the main asteroid belt, you have these things called they're sort of almost, what are they called? Main belt comets. It seems like some of these objects have retained ice, which is not the case for most C-type asteroids. We have no evidence of ice in Bennu, unfortunately, and it probably wouldn't survive the collection process, certainly wouldn't survive at the surface. But it does suggest these may be even more primitive in some ways than the C-type asteroids like Ryugu. So I love this image, and that's one of the great things about having a spacecraft that go to an object and look at it in detail. I haven't actually got my glasses on, but and perhaps at the back you can't see very well all the details. But you could, I'll put this back up at the end of the talk and you can come and have a closer look. One of the things, certainly the people at the front of the audience can see is it's very rocky. Now, the remote observers had predicted that the surface of Bennu was going to be nice and smooth and fine-grained. In fact, it's so rocky, they weren't even sure they were going to be able to land on this. They spent a lot of time mapping it, looking, and I think they found 4 areas that might just make it within their safety criteria. And we'll come and look at those in a second. Another shock they got was that as they got close, is they discovered that Bennu was shooting off particles. I talked to one of the NASA program managers, and apparently this caused a huge headache. There were engineers, the more conservative engineers were saying, we can't go anywhere near this asteroid. It might destroy the spacecraft and sort of ruin the whole point of the mission. Eventually, they got brave and said, no, we're going to go for it. I don't think these particles are coming off particularly high velocity, but nevertheless, it made them very nervous. So as I said, they spent a lot of time looking for flat areas and doing as high resolution characterization of the sample of the areas as they could, and they finally chose one site. And just like the Ryugu samples, they see evidence for hydrothermal activity. So they see clay minerals, they see calcite and dolomite, which you typically find sort of in limestones and things like that. And they see lots of evidence for organic material. They also were surprised, but perhaps they shouldn't have been, that they found rocks that appear to be coming from other asteroids. And, rocks get knocked off one asteroid, and some of them are going to end up on the surface of another one. And it'll be very interesting to see if these really are coming from different asteroids, and if we could sample those things. So I thought I'd quickly show this video of how the sampling works. So if you're into acronyms, this is the mission for you. I'm only going to show you one acronym, but we're getting involved in this. Everything has an acronym. So this sampling, why they couldn't just call it the sampling mechanism, it's the touch and go sample acquisition mechanism, or TAGSAM. And maybe I'll see if I can go ahead. So this head here is about 12 inches across on a 11-foot, 3-meter boom. What it does is it touches down, and as soon as it touches down, it sends a jet of gas into the sample, which knocks up material through these filters, and the coarser material then gets trapped and stored. That's the theory, anyway. What actually happened? Well, here you can see here are different views of the spacecraft, and here's the head coming down onto the surface of the sample, and it looks reasonably flat in this area. So they did a good job of choosing it, and getting closer and closer, getting ready to land, slowing down, and when they land, the anticipation is terrible. Boom, all hell broke loose, and must have given the engineers a heart attack when they saw these videos. Basically what happened, what they think has happened, is that rather than just hitting the surface, it buried itself about 60 centimeters into the surface. And so that when the air came out, stuff was flown everywhere. Luckily, it didn't destroy the spacecraft or damage the spacecraft as far as they can tell. So this is a simulation of what they think happened. So it goes in, and then boom, it lets out the gas, and there's a huge amount of material gets thrown up into the air. But despite the sort of the heartache it must have caused, actually it may have been a good thing, because they think they've got collected much more material than they expected. They were aiming for 60 grams, but as you can see, they got so much material in there that the flaps that were supposed to seal the head here, so this is where this is the sort of the head, and the gas came down here and then would have gone back, sample going out. You can see as they move away from the spacecraft, from the asteroid, you can see material is still coming out of the head. Still, it didn't all come out as far as they can tell, and they were able to stow it safely, and you can actually see, I think the sharp-eyed people can see it was still shedding material even as they were stowing it into the sample holder. So they think they've got much more material than they were originally aiming for, which is great for sample science. We normally only get to play with about 25%. The rest gets archived for future use. So we're going to have much more material to play with. As Mike said, we're going to get some of the first samples here on campus. So the sample is they hope is going to be coming down on September 24th of this year. And this is a sort of timeline for it. It's coming down at the Utah Test and Training Range. That's a huge military area for testing bombs, basically. And hopefully we won't land on unexploded ordnance, but two other spacecraft have landed in this area, and they didn't have a mishap, at least on that account. So as soon as they can, they're going to helicopter out to wherever the sample lands. They're going to open up the canister, get the sample head into and do all this in a clean room, get it into a nice evacuated sample holder, and then fly it to the Johnson Space Center for curation. And things, at least initially, are going to happen very quickly. The hope is that within days of the sample return, we have something to announce, if not publish. And we're going to be sent samples, and we have to turn around good data within a week of the sample landing. So it's going to be that first week of sample characterization and analysis is going to be pretty hectic. And I do worry that if everyone's under pressure, there's going to be mistakes, but that's what they want to do. They're going to, after that initial rush, there's going to be a sort of a more stayed period in which they catalog the samples, send samples out to the various members of the preliminary examination team. We'll be able to do some more longer-term measurements at that point. And they are expecting within a few months to have a large number of the first two manuscripts in what, 3-4 months, 6 months, as well as large numbers of manuscripts. I actually think this is less than I think I've seen something like 50 manuscripts. They already have titles and author lists on it. So they haven't written the text yet and said what the results are going to be, but it's pretty close. Anyway, and then there's going to be, after this initial rush, there's going to be a more leisurely publication of results. But I think there's going to be a lot of people competing to get these manuscripts out at this point. So this is just an illustration of where the samples are going to be going. Most are going to be in the US and Europe to a lesser extent, as well as Japan and Australia, either because these different laboratories do things that we don't do in the US, or because they've had international agreements between NASA and ESA and JAXA, et cetera. I think, I'm not sure if the reason that some of the samples are going to Australia is because they helped JAXA with the Ryugu samples. They landed in the outback in Australia. Anyway, this, as it says, there's about 200 scientists involved in this preliminary analysis. And then after that first 6 months of work by the preliminary analysis team, anyone in the world can apply for samples. So quickly, just what are the scientific aims for this? So the powers that be have come up with 12 major hypotheses they want to address, and each of those has 10 or 15 sub-hypotheses, which the papers are all supposed to be addressing. So one of those higher level hypotheses is, how does the sample compare with observations from spacecraft at Bennu? This is part of the trying to ground truth the sort of remote observations, either with a spacecraft or the telescope, with what we find in the samples. And one of the actually very exciting things is that from the spacecraft, they were finding evidence for very large veins of carbonate, suggesting, which is we see in the Earth, where hydrothermal fluids are flowing through rocks and they're depositing minerals as they grow, as they cool. And so you can see, so this one is what, 2.5 meters across. There's another one up here. I think there's more here. So it really suggests that this body had a very active hydrothermal system going on, which is amazing for a relatively small object. And it may help us understand the processes involved in as the bodies were heated up by radioactivity internally, started to melt the ice, and then that as they got hotter, you started to get this sort of hydrothermal flow going on in the samples. So as I said, this is probably from a carbonaceous type chondrite, which we know are full of organic material. And so, of course, one of the questions we always ask when we come across extrasolar organic rich materials is, does the sample contain organic compounds that could have influenced the origin of life? We certainly find in the meteorites that we think are related to this. We find amino acids, nucleic bases, sugars, et cetera, and some of these have what's called chiral properties. So chirality is where you can't just, and you can do this with your hands, you can't just translate one hand over the other. You have to do a rotation to map one on the other. And this is one of the key properties of life on Earth. They tend to be all either different molecules tend to be either left or right-handed, not equal abundances of both. And we find that chirality in meteorites. Always worry about contamination. We've done our best. So it will be very interesting to see if this chirality persists in the Bennu samples when they come back. As far as we can tell, in Ryugu, what we're finding in the meteorites is not contamination, but you never know. You always have to worry, given how much organic material there is on the Earth. And then, so more broadly, one of the other or bunch of the high-level hypotheses is, what does the sample tell us about the history of our solar system? Going from the pre-solar molecular cloud, which is here, to planetary disks, we have material in meteorites, which we think date both from the pre-solar molecular cloud and other materials that form in the disk. But having these pristine materials is very important. Especially, my personal hope is this is actually an asteroid that we do not have samples of in our meteorite collections. But that would make me unpopular with some people. But I think it will give us yet another window into how the solar system formed and then material was modified once you start to build up big bodies. And finally, I guess this is a more practical thing. How has the sample changed since collection? I mean, that's obviously very important. You can lose volatiles, you can break up rocks and shock them, and you can contaminate them with spacecraft materials and curation materials. So actually, this is, in some ways, this is sort of the first most basic measurements we need to make sure that we don't announce some great new discovery only to discover actually it's contamination. Anyway, it's going to be a very exciting few months in October and November, December. And based on what the PI would like to do, you'll hear very quickly at least some basic characterization of these samples and how exciting they really are. So look forward to September 24th. Wow.
Thank you so much, Colin.
45 minutes, exactly.
It's amazing that we can go get samples from these objects. So I've got some questions here. Is it feasible to have a return mission from a comet in order to retrieve volatile composition? So, sort of, what have you done for me lately?
Right. Well, we have actually had, and I didn't have time to talk about it. In 2006, we had a sample return mission to Comet Wilt 2. It wasn't ideal because it was a flyby mission. They flew by at 6 kilometers a second. If you can imagine trying to collect material at 6 kilometers a second. It was done by having this very low density material called aerogel as the collector, but nevertheless, most of the material, like organic material, was completely chewed up, and only some of the more robust materials survived. There was, in the last round of New Frontiers proposals, there were 3 comet return proposals. I was involved, and George Cody, I was involved with one. George Cody, another staff member, was involved with another one. And we weren't allowed to talk to each other about them, which is hard if you know George. But they didn't get selected. I think there are going to be more comet sample return missions in the next selection, but realistically, we're not going to get back materials until certainly the late 2030s and more likely the 2040s. So I won't be here by then, but stay tuned.
Okay, so I know we have found Mars meteorites on the Earth, but has anybody identified Mars material from the moon?
From Phobos?
No, from our moon. So a meteorite, I guess, that lands on our moon, and then we pick it up.
I think we found some micrometeorites. I don't think we found the large one. We found meteorites on Mars too, or rather, the rovers have. So there is material being swapped between the different inner solar system planets. I don't know of any large meteorites on the moon, but there almost certainly has to be. The trouble is, it's an airless body, and so generally they're going to be coming in at 10, 20 kilometers a second. Most of them are just going to vaporize on impact. But.
So what's the mechanism for chiral excess in organic molecules found in space?
If I knew, I'd get a Nobel Prize, I think. We don't know. I think that's the simple answer. We simply don't know. It does look like it might be associated, or at least it grows as you actually destroy some of the sample, particularly in the amino acids. It almost looks like as the abundances go down, the chirality gets built up. It's never huge. It's only, I think, the biggest one that's been discovered or reported is about 20%. But that's still pretty significant, and it's very surprising. And we really have no idea what's causing it.
So what do you think the most distant object that we'll ever be able to return a sample from?
Ever?
Ever. Let's keep it wide open.
Well, I mean, it would be nice to bring back material from a Kuiper Belt object, I guess. Perhaps your best bet is to, well, actually, we know that interstellar objects are coming through our solar system on a moderately regular basis. It's not beyond the realms of possibility that we could have a sample return mission to an interstellar material coming through our solar system if we can see it early enough and have enough energy to match velocities with it. And that would be truly spectacularly exciting. I know ESA is planning on parking some spacecraft, not for a sample return, but to try and do flybys of objects coming through our solar system.
So how deep do you have to bore into an asteroid to get an unweathered sample?
Well,
Maybe
that's a
maybe
really
we'll find
hard-
out.
yeah, that's a really hard question because you have a lot of turnover in that topsoil of an asteroid. And in fact, so it's called gardening, and they both space weathering and regolith gardening are features that were first observed in the Apollo samples, particularly in the drill cores of the soils, and it can go quite deep. So there may be individual particles that have somehow escaped being at the surface and being space weathered. But I don't think any particles, the surfaces of any particles are free of space weathering. The nice thing is that it's only a few hundred, typically it's only a few hundred nanometers thick, the space weathered material, but for the most damaging space weathering, that's enough to ruin reflected light observations or make them more difficult. But if you have a millimeter or centimeter size sample, it's a tiny fraction of the actual material you have. So for sample scientists, it's not such a big deal. For astronomers, it is.
So what sample collection technology in development do you think will most affect this scientific field?
Well, actually, one of the comet missions that I was involved in, and former EPL director, former EPL staff member who's going to lead the new version of it, they want to actually almost essentially harpoon a comet. So you would actually fire a projectile, a hollow projectile into the comet and get a drill core about 10 centimeters deep. Whether we can bring that sample back completely frozen and unmodified isn't clear, but at least we'll get some sort of idea of how things vary as a function of depth. And that would be very exciting. Otherwise, we have the sort of type of mechanisms that you saw with OSIRIS-REx. Ryugu does something similar. It fires, or rather, Hayabusa 2 did something similar. It fired a pellet into the asteroid, and that knocked material up into the collection mechanism. I think one of the other comet samples is basically has a polisher. So just so these brushes that brushes up material into their collection. If there's anything more radical than that, I'm not aware of it. But that's not really my field.
Okay, I think we'll go with one more here. I think you kind of answered this, but maybe we can be a little bit more specific. If you could sample material from any object in the solar system, which one would you choose and why?
I think it would have to be a comet.
A comet?
I think it would have to be probably Comet 67P, and I can never pronounce the name, that the Rosetta spacecraft went to. And the reason that for that is its properties, its chemistry looks as close as we can get to what our expectations from material that is largely interstellar in origin. It has very high, the water is very heavy, it has very high deuterium abundances. It's, I think, almost 30% by mass is refractory organic material. It has other aspects in its ice composition that suggests it's largely unprocessed interstellar material. And that would be truly exciting to have unprocessed interstellar material in the laboratory. Would be just, I'd come out of retirement for that. If my wife would let me.
Well, thanks so much, Conel, and join me with a round of applause for Conel. Please stay tuned for our next NLS. I think will be happening sometime later in June, and announcement will come out shortly. And I think you can have access to Conel if you've got any more questions.
And I promised I'd let people come and look at that video, which I love, of Bennu going round and round. Oh, come on. There we go.
Thanks, everyone. Have a great evening.